Okay. Hello everyone, welcome to another Learning Glass session. Today we'll talk about another aspect of thermodynamics. Specifically, we'll talk about refrigeration, a very important component of our comfortable lives. The basis of this whole design is thermodynamic principles, and it ties together a couple of the things we've been talking about. I guess like steady flow devices, first law analysis on steady flow devices, heat engines in reverse, and properties of substances similar to the steam tables we were talking about for water properties. We're going to all substances behave like that, and in the case of refrigeration, we want to have a nice substance that has properties that get cold. And when we apply this ideal vapor compression system process cycle on this refrigerant working fluid, we can get what we want, which is cold. Okay, so refrigeration using this cycle looks like there's a vapor compression process. The compressor is one part of this cycle, so this is what a typical compressor would be, of course. So work into that device is needed to change the state of this working fluid. So that's typically the first step in this process, where let's say you have this typical refrigerant at negative 25 degrees or 25 degrees-ish. This would be the kind of the end of the process, but let's call it state one, as most of the textbooks do. And then, so state one would be going through the compressor to reach a higher enthalpy state and a higher temperature to keep the cycle going. It's refrigeration. So you fridge and then you refridge. So this second step, the second state is coming out of the compressor. Then this working fluid refrigerant gets run through another heat exchanger type process, where from this high pressure, high temperature state, you transfer some of the energy out. So if this was the back of your refrigerator, you would, this is where this transfer would occur. It'll be a transfer from this hot compressed working fluid refrigerant to the room, which is what all reverse heat engines require, some heat transfer out at high temperature, relatively high temperature to this. Then you undergo a process unique to refrigeration, which is where from state three, after this condenser process where the heat transfers out and you reach a saturated liquid state, you expand. So this would be an expansion valve where delta H equals 0. That's what's unique, is that you're doing this expansion process such that there's no heat transfer, there's no work transfer. So the enthalpy at the beginning is the enthalpy at the end, and there's going to be some entropy increase. So that's the throttling process, and okay, good, just enough space. And so the next step is state 4. This is the whole application of this whole cycle, is to refridge, fridge, then refridge. Here's the fridge part, where you have another heat exchanger. Of course, in both of these cases, you have this is some transfer to superheated to some condensation process to go to the saturated liquid line. Then here you're still at the you throttle somewhere into the mixture. Then what this process is doing is that you have a cold refrigerant that's been throttled, so when you expand it, the temperature drops. Then you run it through this heat exchanger such that energy comes in. If you're at negative 20 Celsius, anything hotter than negative 20 Celsius transfers heat into this working fluid. So that would be this heat transfer in to the system, but remember it's low temperature. So you're able to freeze ice by doing this. If you had liquid water in the surroundings, that liquid water transfers energy into this negative 20 degrees Celsius working fluid. That's enough to freeze the water. So that's what we're doing here. We're getting a working fluid much colder than anything else. By doing that, you can that's what this refrigeration application is all about. Okay, so let's draw this on a temperature enthalpy diagram. This is the enthalpy. This is the temperature. This process operates around this saturated vapor dome, but we're not working with steam here because steam doesn't get cold as we want. We want to freeze ice. So to freeze ice, we need to find a magic substance that can get very cold under this process, and that's what the refrigerant is. There's many different types. Freon is the brand name for chlorofluorohydrocarbon type thing that did this job pretty well. The problem is it had environmental problems, so that's no longer legal. There are other replacements for that that we have to use now. So this would be state one here. It would be on the saturated vapor line at the borderline between a mixture and a pure gas phase, superheated vapor. And what you do is you compress it at constant entropy. This is an ideal vapor compression process. This is one of the ideal parts of it. It's an isentropic compression into the superheated vapor stage. This would be state two. This would be state one. Then this condensation process is by exchanging heat with the surroundings, you can go back to this boundary of the saturated vapor, but at a higher temperature. So we're following one of these pressure lines, and you follow this constant pressure line, and you start changing phases here, and you end this condensation process on the saturated liquid boundary. Then the throttling process is carried out such that at constant enthalpy, but you gain entropy, you expand the gas, you expand this the saturated liquid into a mixture. So this becomes a saturated mixture down to this original working pressure at the evaporator stage. So this is the evaporator, and then this is the whole main activity of this whole design is to boil this refrigerant. It starts off as a saturated mixture at state 4. You use something hotter than negative 20 degrees to boil this refrigerant vapor liquid mixture all the way back to its borderline on the vapor phase. So this is a reverse heat engine. You have to transfer heat at the high temperature, and if you want this low temperature heat transfer, if you're using a cycle, you have to have some high temperature. So that's how this process looks like on a temperature diagram. You're working in the steam dome of this refrigerant. One of the things that makes the refrigerant a refrigerant is that it gets really, really cold. So this temperature, typical temperature, would be negative 20 Celsius, as I showed here. And this is high pressure, this is low pressure. Typically less than 1 atmosphere, much higher than 1 atmosphere. Okay, so all of those properties you would need to analyze this problem is given by a table that's like the steam tables, but it is for this a working fluid refrigerant rather than the water. Okay, so if we were to apply the first law to each of these stages, you would have the first stage isentropic compressor. Let me get another marker here. So the first law for that is the work into the compressor is balanced out by some change in enthalpy, steady flow device, and the mass of the refrigerant stays constant throughout the cycle. So you don't, if you have a normal refrigerator in your kitchen, your AC in your car, or in your house, you don't change the refrigerant often. It is consumable, but it's only because it leaks due to wear and tear, or it's very slow process to replace that. It doesn't get consumed, it gets recirculated in the cycle. And what you're doing here is you're going from a saturated liquid at state 1 on this boundary line to superheated vapor. Okay, so that would be the analysis of the compression stage, and all of this, depending on what you have, you would need to consider different ways to analyze the problem. The condenser stage is some heat transfer out of the refrigerant and this is Q out, or in terms of a heat engine, it's the QH stage. It's the high temperature energy transfer by heat stage. And then the expansion by throttling the thing about this is that if you apply the first law, you would say that there's no heat transfer, there's no work transfer, so that leaves that H3 is on first estimate in this class. We're just going to say that there's no enthalpy change. And another thing is that S3 is smaller than S4, so S4 greater than S3. And this is, oh, I didn't write the states here. So here, this is condenser would be superheated to saturated liquid. This would be saturated liquid to saturated mixture. Okay, now the whole point of this refrigeration cycle is to fridge. That will be the process going from 4 to 1. It's called the evaporator, which is due to the fact that we're using this low temperature property of the refrigerant such that after throttling it gets really, really cold, but it's a mixture of liquid and vapor in this line, this refrigerant line. And in the heat exchanger, what we're doing is, at low temperature, taking energy from some refrigerated space out of the refrigerated space into the refrigerant to boil, complete the boiling. So it starts off at low temperature, it undergoes phase change of boiling, but it's a refrigerant, so it's really, really cold, and that temperature stays constant because of the phase change. Okay? So the evaporator is where the fridging occurs. So like I just said, you're boiling refrigerant to keep refrigerated space cold. That's the whole point of this, is to refrigerate. So the fridging is that evaporation process of the refrigerant by taking energy out of the refrigerated space at cold temperature. So the first law would be the Q in. It's not the refrigerated space we're directly analyzing. It's what happens to the working fluid of this cycle, the refrigerant. So energy comes into the refrigerant, and we don't know the temperature according to the first law. We would have to do more analysis from this form of the first law to get the temperature. And this is a reverse heat engine. This is a QL. This is the whole point. This is what we want. And what we're doing is we're going from a saturated mixture to the borderline of the steam dome. So that's how you would analyze the first law. And for an ideal case, this is pretty much what we need to analyze most of the system. And like I said, we don't directly know the temperatures from the first laws. We would either have to have something given or analyze the properties of the state. How do we know the state? Well, the enthalpy tells us about the state. So enthalpies is one thing. So if we knew the enthalpy and the entropy, that would pin everything down and we can get the temperature from a table. Again, we're in this mixture region of either saturated mixture or something on the borderline or something in the liquid phase. We can't use the ideal gas equation unless we're somewhere in this superheated vapor region. So we're going to have to rely on tables to get the properties of the refrigerant working fluid if we're not in the ideal gas zone. So that's why it's important to have the access to this R134A table, for example, in many cases, and because that keeps track of the state of the working fluid in this region. There's no equation to capture all these properties. You need a table. Okay. So to evaluate the performance of this, there's something called coefficient of performance, which is similar to an efficiency. The reason why it's not called efficiency is because it's greater than 1 theoretically. In real life, it's harder to be greater than 1 just because things are not performing ideally. But in our ideal analysis, we'll see that it's often greater than 1. So beta, coefficient of performance, is what we want, which is some Q in at low temperature versus what we have to pay. In this case, it's just the work in at the compression stage. The net work in, which is only one stage, there's only one mechanical work process in this. So that's what we have to pay. We have to put work in to keep this cycle going. And if we express this in terms of enthalpies, that's what we will get. Okay, so let's do a quick analysis of some example analysis that we would do if we were given some properties. Okay. So, I guess I'll do it up here. This is the ideal vapor compression cycle. So let's say, for example, we are given that the refrigerated space
Sorry. You know what the office for the IVs, is it in this building?
yeah, no, it's over there.
I'm sorry?
Can you ask this man over here? He knows. Trying to broadcast here. Okay, so if we're given that the refrigerated space is 0 degrees Celsius, so refrigerated space at 0 degrees Celsius, with that, what one good assumption to make, it's not perfect assumption, but if you're saying that you have a freezer, you're trying to keep it at 0, you can connect that back to the refrigeration cycle. What you're saying is that assuming that there's not a lot of heat loss, if this is at 0 degrees Celsius, that means that when you're at this refrigeration, so this is the refrigerated space here. Like you're pretty much having a heat exchanger where this is the refrigerated space. Here's your ice cubes here. And the energy from the ice cubes is coming out of the ice cubes into the refrigerant. And so there's two things, that assuming there's no energy loss, and assuming that there's a phase change going on here, this will be at a constant temperature. So you can assume that this is basically telling you the temperature of the refrigerant at the evaporator stage. So this would be, instead of being a colder than it could be, what you're saying is that if the refrigerator is 0 degrees Celsius, you could assume that T4 equals 0 degrees Celsius. And in an ideal case, it's a phase change going all the way until this border, so the temperature does not change. So that is the temperature of T4 and T1. That's one assumption you can make. Also given that after the condenser, basically T3, after the condenser, which we can call T3, this equals 26 degrees Celsius. Okay, and you're also given the flow rate of the refrigerant, which is constant. It doesn't leak out. It's a closed system. A typical flow rate of this refrigerant is 8 grams per second. Is that, no, 80 grams per second. So given that, we have enough to start our analysis, and that this is refrigerant. This is R134A. R134A flowing at this flow rate, at this temperature at the evaporator, and that temperature after the condenser, we can start doing stuff. And what we'll do is look at the tables. So use table A10 R134A tables. To get the enthalpies that we need, and maybe the entropy that we need, and so that we can analyze the coefficient of performance or any other part of the analysis. And what we're given is temperatures, which is good. The other thing that we can, that if we're using this ideal vapor compression cycle, is that, so what we know so far is that the temperature at the evaporator and the temperature of the condenser, but starting from the temperature at the evaporator, what that tells us is that the that this temperature is there. Another thing we know is that from the ideal process, this is saturated mixture or saturated liquid. So it's somewhere on that saturation line, okay? How do I know H2? Well, let's start with the evaporator. So at the evaporator, so we know that T1 equals T4 equals 0 degrees Celsius, and we know that it's a saturated, that T1 is saturated mixture, T4 is saturated mixture, so this is saturated mixture is H4, and saturated vapor is a state of H1. So those two pretty much pin down the enthalpies. At 0 degrees Celsius, we know that we can pin that this is on the vapor line. There's only one possible value at 0 degrees Celsius, so that would give us H1 equals 247 kilojoules per kilogram of refrigerant. And then for H4, we need to know the quality of vapor versus liquid so that we can take the weighted average to find the saturated mixture. We don't know that, but what we do know is the temperature after the condenser is T3. So, so T3 equals 26 degrees Celsius, but we know that it's a saturated liquid at H3. So that pins down those two properties. It's on the borderline. There's only one possible value at 26 degrees Celsius to be on that borderline. If it's saturated liquid, there's only one H3 possible. It's 0% quality. So that pins that down. That is known. And what we know that throttling, that H3 is approximately H4. So basically, by knowing the temperature at the after the condenser, we know that it's saturated liquid, we know the enthalpy there, and then that gives us H4. So H4 equals, what did I get? H3, let's say that this is 86. So that's what H4 is. And so that allows us to find the QL. The heat transfer at low temperature, it's this known mass flow rate. This known mass flow rate times this enthalpy change, and if you plug those in, you would get that the low temperature enthalpy is that. So you know that. So H2, how did I get H2? So now we're going to try to analyze the so let's forget about the condenser. Let's analyze the compressor. So if we know enthalpy 1 is given, temperature 1 is given, that's 0 degrees Celsius. We know that it's a saturated liquid, so that pins down that we can find everything else. On that saturated liquid line, only one possible value at 0 degrees Celsius. So that means we know the entropy. So similar to here, where we know T1 and we know H1 is a saturated vapor, or we could just say saturated vapor here. Those two independent properties allow us to pin down H1 and S1. Okay, that's good. So, if we know S1, that we can say if this is an isentropic compression, we can know entropy, and I think there's another variable, the pressure probably, after compression. I think I didn't write. Let's say we're given, I'll double check this, but we might know P2 is given. I don't know, let's say like 6 bar or something like that. I think that's what we needed to know, that if we know the entropy at state 2 and the pressure at state 2, we can find H2. And I got 265. Because in my example here, we have H2, and we needed something for that, I believe. Maybe by going back to the condenser, but okay. So let's say we have H2, then we can find the work in is the mass that we know, H2 that we just found, and the enthalpy at 1 that we knew. And plugging those in, that gives you 1.4 kilowatts. So that's good. So in this case, if we were to plug in to the coefficient of performance, that would give us 9.3 coefficient of performance in this case. Okay, so that's one part of the analysis. Another note is, side note, that you probably will hear in your engineering life, or even your home life, is tied to the history of refrigeration. So we found, using the properties of the steam tables for R134A, and based on what we were given, that you can find, you can analyze the system and the coefficient of performance and such in this case. So on a side note, refrigeration capacity has a specific meaning it's basically QL, but in tons of refrigeration. That's the units. And the units are, so 1 ton equals 211 kilojoules per minute. So tons of refrigeration is kind of a power in minutes. It's a weird thing, but you know, it has a history. And so what it literally means is, so if you were to put this in to the QL, you would get 4 tons capacity. 4 tons-ish. convert that to from kilowatts to kilojoules per minute. That'll give you the tons. And what that means is literally that 4 tons, 1 ton of ice frozen per minute. That's the history of this unit, where what we were trying to do was freeze ice so that, because in the initial days of refrigeration, only one big ice house had a refrigerator. And that ice house was used to make ice so that that refrigeration can be distributed to other people from the ice house, and then people can use the ice. So this whole engineering analysis was in terms of tons of refrigeration, which means literally how much ice you can make with this refrigerator. Okay, so that is an example of this analysis. Double check how I got H2. I will double check myself. But with that, thank you, and we'll talk next time.